Hi, welcome to the Radio Joe Project, Citizen Science Training Modules, and the Sunrise Project. My name is Dr. Samantha Blair, and I am a professor of physics and astronomy at Dalton State College, as well as a member of the Radio Joe team. These training modules are a partnership between the Sunrise Mission Team and the Radio Joe Project. We acknowledge contributors to these modules as well as our funding sources of support, without which we could not do these projects. And so this training module is module 0.1, in which we're going to talk about the solar interior. Prereqs for this, being able to understand the material in this module, some general science, some mathematics, some basic understanding of scientific notation, the electromagnetic spectrum, speed, wavelength, frequency, the energy of waves, understanding how to read a graph, and hopefully you went through training module 0.0. After a brief review of the sun's interior layers, we're going to discuss the processes that happen in each of the regions, and we're going to include an overview of the basic nuclear reactions that power the sun. So, in this first slide here, this is a diagram that has a cutaway of the sun showing the various layers and structure of the sun. The interior here consists of the core, where the nuclear reactions are happening, and the radiative and convective energy transport regions, all right? The surface of the sun is called the photosphere, where the gas becomes optically thick, all right, which means it's opaque to visible light. That's why we can only see to the surface of the photosphere. We can't see to the interior of the sun, all right? The sun has that very distinct circular spherical shape because of this opacity of the photosphere. Sunspots occur in the photosphere, so the sunspots are on the photosphere, and above the photosphere are the thin layers of the chromosphere, the transition zone, and then the thin outer hot tenuous layer, which we call the corona. Now, the corona is also related to the solar wind, which are the charged particles that are leaving the sun. This second cutaway of the sun, all right, shows the interior density of the sun is about 150 grams per centimeter cubed, or 150 times larger than water. However, the density becomes very, very small at the photosphere. So demonstrating the near emptiness of space. Space is very cold and very empty. The sun is a giant ball of hydrogen and helium gas that's held together by gravity. All right. The weight of the sun is held up by the outward pressure caused by the nuclear reactions, and this force balance keeps the star stable over a long lifetime. Okay. And you can see here that the surface temperature of the sun is 5,800 Kelvin. We have the interior density, the photosphere density, and then we have the average density of the sun at 1.4 grams per centimeter cube. Now, nuclear fusion is the process or the energy generating process inside all of stars, all right, all stars that are out there. And the basic nuclear reaction for solar-like stars is the proton-proton chain, where we have 4 hydrogen atoms that combine to form helium and give off energy. All right, the net reaction shows that the total energy given by nuclear reactions is 7 high-energy gamma rays and 2 neutrinos. Conditions for these reactions to happen require 15 million kelvins and 100 billion atmospheres of pressure. And those can really only be achieved inside of stars. Stars are our chemical factories. So you see here we have 4 hydrogen atoms that are fused together to form a helium, which gives off this energy. Taking a closer look at the proton-proton chain, you can see the time scales are actually quite long. All right, we can see this diagram shows the reaction chain for the generation of helium-4 from hydrogen. Notice the same reaction must happen twice to generate 2 helium-3 atoms that then make a helium-4 atom. Also notice the time scales are quite long because of the light charge repulsion, all right? 2 light charges don't want to come together, but under really high temperature and really high pressure, they can be forced together. The protons take a long time on average to react. So each red-orange energy explosion symbol that you see on this diagram represents the release of a high-energy gamma ray, 7 in total, plus 2 neutrinos that are given off during these reactions. In terms of nuclear energy, all right, how is energy generated by these reactions? Well, Einstein's famous E equals mc squared comes into play here, all right? And that's where mass is converted into energy. So for each atom of helium-4 that is created in the proton-proton chain, a small amount of mass is lost. Using the E equals mc squared, the mass loss generates a tiny amount of energy. So how does the sun generate so much energy? For each second, 600 million metric tons of hydrogen are converted to helium inside the core of the sun. Let me repeat that. Each second, 600 million metric tons of hydrogen are converted into helium. Okay? And so that's why the sun is releasing so much energy. If you look at this diagram, we've got 2 diagrams here. We have another cutaway that shows our core. We have a radiative zone next to the core, and then we have the convective zone out near this region that backs up to the photosphere. And on the right-hand side, we have some graphs. And the graphs give us a profile of the structure of the sun, all right? We want to notice that the energy generation rate, and we want to notice the energy generation rate and luminosity graphs there. All right. This tells us that all of the energy comes from nuclear reactions happening in the core. Okay. All happening inside 20% of the radius of the sun. So the radiative zone carries energy outward by the process of electromagnetic waves as radiation in the radiative zone, which is right outside the core. Then as the temperature decreases and the opacity of the gas increases near the surface of the star, convection in the form of those circles with arrows you see there in the convective zone, convection energy transport becomes more efficient. The outer 20% of the sun is convective, allowing for energy to reach the photosphere surface of the sun. Okay, and so photons move through the sun and are absorbed, re-emitted, and absorbed over time, okay? And finally reach the edge of the sun and are released. So our radiation zone is an energy transport region. No new energy is generated, all right, in the radiation zone. It's all generated in the core. Energy from the nuclear reactions in the core are transported through the radiation zone by random walk of photons, like I said, as they're absorbed and emitted. The overall flow of energy is outward, all right? The neutrinos, however, because they only weakly interact with matter and they're practically massless, neutrinos generated by the nuclear reactions in the core travel outward at the speed of light without any interactions. Okay? So we see our convection zone there. We see the photons doing the random walk, and that white pathway shows them being absorbed and re-emitted, absorbed and re-emitted. But the neutrinos speed out. So if we look at the surface of the sun or the photosphere, which is that outline of the sun that we see, basically, looking at it at a distance or at low resolution, it appears smooth. But on higher resolution, we're looking at it more closely, we see a pattern on it. All right, on the left in black and white, we can see it. And then in the middle, we can see a color image of this pattern. And this pattern is what we call granulation. All right, because it looks sort of like grains. All right. And this is evidence of convection of gas beneath the surface. And as you can see here, we have gas that rises. Hot gas is going to rise, heat rises, hot gas is going to rise, it's going to cool, and it's going to sink. All right, darker gas descends. And the size of each of these blobs here is about the size of Texas. All right. Now, if you look at the image to the right, you can see that the edge of the photosphere is dark and the center of the sun here is brighter. So what we call that is limb darkening. All right. So you can look at the center of the sun and you're looking deeper into the photosphere. When you're looking at the edges of the sun, all right, they appear darker because you're seeing the cooler gas that's closer to the surface. All right. And so that's what you're seeing when you're looking at the photosphere. So that's our journey through the sun. And there's some good resources here for you if you're interested. We've got heliophysics or solar physics from the NASA Marshall Space Flight Center. We have Solar and Heliospheric Observatory information, SOHO from NASA. There's NOAA Space Weather Prediction Center. There's the Australian Space Weather Forecasting Center, and then there are just some space weather sites there that you can look at if you're interested. I hope you enjoy this, and I hope you enjoy the next module, training module, and happy observing clear skies.